Today on How It's Made. Cars, grocery carts, rapid tooling and prototyping, and collectible coins. The automotive industry has seen a lot of changes in recent years. More and more robots are replacing workers on the assembly line. And it isn't just cars and trucks coming off the line anymore. Today's Hot Wheels are sport utility vehicles and vans. In the plant's body shop, they begin by putting together the front structure of the van. It's made up of the radiator support, 2 side rails, and clips on the front of those side rails for the bumper structure. Then they put this front structure onto the automated production line. Meanwhile, robots weld what's known as the ladder assembly. It's the backbone that supports the floor and sides of the van. It contains, among other things, the pockets that will hold the seats. Now the robots take the front end structure and the ladder assembly and weld them together. Elsewhere, robots work on the body panel for the passenger side of the van. The entire panel is made of one piece of galvanized steel. The robots weld reinforcements onto the panel so they can later attach interior finishing and other components. A transfer device swoops down and transfers the panel to the next station. The driver's side body panel, coming off another welding line, is headed there too. At that next station, robots have already installed an underbody with a floor panel on top of the ladder assembly unit we saw earlier. Now the robots weld the body side panels to the underbody. They also weld inner wheel wells to the body side panels. Then they weld on a roof. The van then rolls into the area of the body shop called closures. That's where they install the lift gate, the hood, and the doors. An inspector checks the gaps around the hood, looks for dents and dings in the body, and makes sure the doors are flush with the side panels. He marks any areas that need repair or adjustment with removable ink. The engines arrive at the plant already assembled. Workers just have to install and adjust a few components. Meanwhile, the van is off at the paint shop and then goes to the trim shop for glass, handles, and interior components. In the chassis department, the engine, transmission, rear suspension, and brake assembly are installed from underneath. This part of the assembly line has 2 tiers. The van goes on top, the components on the bottom. The machines that install the components have long pins that fit into holes in the van's underbody. This positions the components with precision. Workers hook up the gas tank manually. The seats arrive ready-made from a nearby factory. They simply clamp into place in the seat pockets that were welded onto the ladder assembly earlier. An automated machine mates the tire to the wheel rim. Then it inflates and balances the tire. Workers mount the tires, starting the nuts by hand, then tightening them with tools. Now the van comes off the carrier and goes full weight on its wheels for the first time. Workers start up the ignition and run the van through a series of tests. It's taken the plant about 24 hours to produce this vehicle, which will soon be on its way to a car dealership. Geomatics is a high-tech science whose objective is to gather geographic information, then study and use it. The tools of geomatics range from cartography to remote sensing to satellite imaging. We wouldn't be able to study the environment or monitor and develop our natural resources without geometric data. An Oklahoma grocer invented the first shopping cart back in 1937. He noticed his customers stopped shopping once their handbaskets became too heavy to carry. His basket on wheels became a rollaway success. This factory makes about 50 different models of shopping carts. They're built with heavy-duty steel and carbon wire. A single cart is made up of more than 150 wire pieces of various lengths and diameters. Automated machines bend the wires to form the cart's numerous components. To make the cart's basket, a worker uses a guide called a jig loader to line up the wires in a mesh formation. Then a machine automatically spot welds them together. The next machine applies 20 tons of pressure to bend the wires into a basket shape. A robot welds the sides of the basket. A worker then trims off the excess wire. An automated machine bends a piece of wire to form the handle of the shopping cart. They make the frame for the base of the cart, called the chassis, out of one thick tube that's almost 4 meters long. A robot welds the chassis using soldering wire melted by an electrical current. This creates a very strong joint. A die machine punches out casters that'll hold the wheels. They're made of thick steel for extra strength and durability. They spot weld the casters to the chassis. They clean the cart's metal components in a bath of soap and acid. Then they electroplate the metal with nickel, then with chrome as a finishing coat. It's finally time for the cart to take shape. They rivet the wheels to the chassis, then install the bottom rack. The basket comes next. They print the warnings on the plastic panel for the collapsible baby seat. Then the seat goes on, along with the plastic corner bumpers. They print the store's name on the handle inserts. The handle goes on last. After some final adjustments and a quality control check, The newly minted shopping cart is ready to roll. Every machine, from your vacuum cleaner to your car, is made up of a series of parts. Those parts are designed by specialized companies. They first build a prototype, then make the molds or tools needed to manufacture the part. They design the part in 3D on the computer. The computer then guides the machines that construct the prototype. One method divides the 3D drawing into cross-sectional layers just a few thousandths of an inch thick. It feeds this information to a laser that's directed at a tray filled with a light-sensitive liquid resin. The laser's light hardens the resin in the shape of the part, layer by layer, eventually constructing the prototype. They rotate the prototype under ultraviolet light for a few hours to cure the resin. Then they polish or paint the prototype according to the requirements of the design. Another prototyping method works much the same way, but uses a fine powdered plastic instead of resin. The computer guides the laser to melt the powder in the shape of the part, again, layer by layer. They extract the hardened prototype from the unmelted powder. Another method doesn't use a laser at all. The computer simply guides machinery to carve the prototype out of a hard material such as wood composite. Once a prototype is ready, they use it to construct a model of the part out of a very durable resin. They'll use that model to make a mold, then they'll use that mold to cast the part out of metal. The resin model dries at room temperature in 24 hours. Its surface must be smooth or else the mold will have defects. They attach channels that will guide the molten metal into the mold. Next, they fill the model with a mix of sand and a binding agent. They smooth out the surface, then number it for tracking purposes. The sand mix takes about 15 minutes to harden into a mold. Now they can finally cast the part. They carefully pour in the molten metal, in this case magnesium, heated to about 700 degrees Celsius. They block the hole with sand to prevent the metal from reacting to the air. The metal takes about 10 to 20 minutes to harden depending on the size of the mold. They crack the mold open on a vibrating conveyor. They use a plaster mold to cast parts that require a better surface finish. Workers position a box around the prototype to contain the plaster. The mold goes into an oven at about 300 degrees Celsius. It takes 48 to 72 hours to cure, but it's not ready for casting just yet. Workers first have to pierce some holes in it to let all the air escape, or else the metal won't flow into all the crevices, and they have to put in filters to keep out impurities. They strap the two halves of the plaster mold together, securing them with metal screws. Workers carefully pour in molten magnesium, using a special gas to prevent the metal from catching fire. Again, they seal the opening with sand. It takes the metal anywhere from 20 minutes to an hour to cool. Then they break open the plaster to remove the metal part. They cut off the channels through which they poured the metal. Then they polish the part using grinders and sanders. Then they paint it using special spray paint that adheres to magnesium. The part is finally finished. It takes several weeks to prototype and tool metal machine parts. When you think about it, Even the machines that make these parts are made of parts that were made like this. The Royal Canadian Mint makes all of Canada's coins. Circulation coins, the ones we use for money, bullion coins for investment, and collector coins, high-quality gold and silver collectibles that commemorate Canada's heritage. The first people to make coins were the Lydians in Asia Minor in 640 BC. About 40 years later, the concept spread to ancient Greece, where coins often featured an owl, the symbol of the goddess Athena. Around 500 BC, the Chinese invented coins made of cheap metals like copper instead of gold and silver. Today's currency coins are still made of copper, nickel, and other inexpensive materials. The Mint manufactures collector coins using sterling silver as well as sterling scraps left over from making other coins. The silver goes into a casting furnace at 1,150 degrees Celsius. The melted silver is cast into a continuous bar about 4 centimeters high by 12 centimeters wide. A machine cuts the continuous bar into individual bars about 80 centimeters long. Each bar goes into what's called the roughing mill. The mill's 2 rollers squash the bar flat, using up to 8.6 metric tons of force. It takes up to a dozen passes to flatten the bar into a strip just 12 millimeters thick. A machine called the finishing mill thins the strip out even more to what will be the final thickness of the coin, anywhere from 0.7 millimeters to 4 millimeters, depending on the denomination. Next, the blanking machine stamps out blank coins. The silver that's left over, called sisal, goes back into the casting furnace where it's melted down into fresh bars of silver. The next stop for the blanks is the rimming machine, whose spinning wheel presses a raised edge or rim on each one. The blanks then go into a tub filled with water, cleaning solutions, and steel beads. The beads act as an abrasive agent, smoothing and polishing the blanks. After a 20-minute cycle, they empty the tub's contents into a sifter to separate the blanks from the beads. Workers then towel dry the blanks by hand. This ensures there'll be no water stains on the coins. Throughout the coin-making process, as the silver is worked, it becomes brittle, so brittle that it could easily break when struck. That's why at several stages the metal goes through an oven called an annealing furnace. The coin design comprises artwork or a photograph or a combination of both. This coin will feature a photograph of Queen Elizabeth provided by Buckingham Palace. The artist uses a computer program to design a collage of various elements. Once the final design is approved by Mint officials, the process of engraving can begin. They take a plaster disc that's 27 centimeters in diameter. The computer guides the engraving machine to turn the one-dimensional computer design into a three-dimensional version in rough detail. This creates a plaster model of the design in the negative. They now use this negative to cast a plaster positive. An artist then enhances the detail by hand. Once that's done, they cast a negative plaster mold. From that, they then cast a positive mold, this time in rubber. From the rubber, they cast a negative mold out of hard black epoxy. They mount the epoxy model on a machine called a pantograph, which is essentially a reducing machine. It traces the model and cuts a version 1.5 times smaller in brass. This reduction process takes 36 hours. Then an engraver takes the brass model and fine-tunes the design under a microscope. At this stage, the engraver also adds the lettering, noting the year, the denomination, and the country of issue. Then comes another 36-hour reduction process. They reduce this brass model 1.5 times to create what's called a matrix, a negative model made of high-grade steel that's the final size of the coin. Then they strike the matrix onto a block of steel, which creates a positive called a punch. Then they strike the punch onto another steel block to create a negative called a die. The coins are made one at a time in the coin press. There are 2 dies per coin, one for each side, positioned above and below the blank. They strike simultaneously, not once but twice, to create a high-quality impression. Not at all like circulation coins, which are struck just once on high-speed machines that make several hundred coins per minute.